So we just concluded about the fundamental particles. So fundamental particles are lepton in the quark family. The leptons, what are the leptons we have? We have the leptons, electron, electron neutrino, muon, muon neutrino, and tau neutrino. What is the symbol of electron? That is this is a symbol, okay? And actually the charge of electron is also a constant, which we also represent by E 1.6. So when it is written -1, what does it mean? It means relative charge. It's not the actual charge. It's a relative charge of, because actual is 1.6 exponent minus 19 coulombs. So this is a relative charge, that it is -1, relative charge -1, or you can also say minus E is better to remember. And the electron neutrino is 0, tau neutrino or muon neutron also have 0. And their antiparticles, positron, anti-electron neutrino, anti-muon, anti-muon neutrino, anti-tau, and tau, anti-tau neutrino. So these are the symbols for their antiparticles. And these are the particles. What about the concept, like the characteristic of the leptons? Leptons are the lightest group of particles because, as you can see, their mass, when we compare the mass of these particles, it's lighter as compared to, or it's less as compared to other particles. They have a spin of half. Here we will not discuss about the spin, because spin of the particle can be half or it can be one. I will give you, you don't have to go in like exam point of view. You are not supposed to learn the spins half or one. So what does it mean? But I will just explain the idea. But you, as I mentioned, you don't have to memorize this or learn. Look, let's say you're, this is the face of the particle and you see a letter A. When we say spin is half and spin is one, if this particle rotate 180 degrees and you see the same face, like you see the same letter again, example, you see the same type or same face again. What we call that particle, we say that it has a spin of a half. But some particles, when they rotate 360, and this is usually what happens. Like example, let's say you're sitting in a, like you're in the country. Let's say someone is observing from an international space station. So when the Earth will rotate 360 degrees, then only he will see you again. So means what is the spin of the Earth? The spin of the Earth is like it will cover 360 degree, or I can say +1. Like when it cover one complete revolution, then you will see the same phase. So we call that as a spin 1. Spin half means when it rotate 180, you see the same thing again. So again, as I mentioned, exam point of view, you don't have to learn this point, but this I explain as a, you should, as a knowledge, but not for exam preparation. Okay. They are acted by a weak nuclear force. So there are two types of forces are there. One is called a weak nuclear force. Another one is a strong nuclear force. A strong nuclear force act for a short distance. And like example, if I say this is a nucleus and there is an electron. Let's say this is a hydrogen atom. Hydrogen atom consists of proton. Proton is not fundamental. Proton is made up of up, and down. So the nucleus does not allow this proton to leave. So when the nucleus is holding this nucleon or this proton inside the nucleus and does not allowing it to leave, what kind of force nucleus is exerting? Nucleus is exerting strong nuclear force. Strong nuclear force act for a short range, and the main thing is it is holding the particles together. And strong nuclear force can be attractive, can be repulsive as well. But the force which is holding the electron, so that this electron, the nucleus is also applying a force on the electron. So nucleus is applying force on the proton so that it will remain inside, and nucleus is also applying force on the electron to pull towards the center. What we call this force, we call that as a weak nuclear force. So electron is a lepton. So usually what happens, these lepton, they experience a weak nuclear force. Simple way to understand is what is happening within the nucleus is strong. What is outside the nucleus is weak. Anything which is outside the nucleus, weak. Anything which is inside the nucleus, strong. So the leptons, which are electron or electron neutrino, tau or tau neutrino, and muon neutrino, so they experience a weak nuclear force. And they are fundamental particle, so we cannot further divide. So according to the current model of the particles which we have, electrons are the fundamental. Maybe in future you may find that you are able to break down this electron into further. Yes, any doubt, Subhan?
Sir, where are these muons and tau present with the electrons?
They are not present with electron. These particles are normally produced when the interaction happen, when electrons are colliding. So these particles are not originally present in a structure. What happened? Let's say the proton and protons are colliding with each other. When when the particles collide, it releases energy. That energy converted into a matter, and the particles which are produced during this interaction are these particles, such as muon neutrino, tau neutrino. Electron neutrino is also produced during interaction. So these particles are not making up the atom, but these particles are produced during interaction of the particles, other particles. But we are
Sir, so
not
these are
able to.
temporary particles, like momentary. They only exist during the interaction.
Yeah, they exist during an interaction and absorb, or they are detected also. It's so, or maybe most of these particles you will find in the space, like cosmic radiations, because in the space there are lot of interaction between the particles, because sun is also emitting out a solar flare, which we call like a beam of the particles which are directed towards the earth, but they are deflected by the earth magnetic field. So these particles have these like muon, tau. So most of these particles we have most of the matter is there on earth, but in our space we have most of these antimatter and antiparticles as well. Is it clear? So you find these particles not as a making up an atom, but produced by interaction of different particles or change of energy into matter. And every lepton has a number. This is a just an identity. Like example, you have a roll number in your school, your classroom. You have a roll number or a serial number. So every lepton is given a serial number plus one. Every lepton. So even it is a electron neutrino, muon neutrino, tau or tau neutrino. What is the serial number or the lepton number? All of them will be plus one. All of them. This does not means the charge. Plus one does not mean the charge. Plus one is just a serial number for these particles. And for anti-lepton, what is the serial number for anti-lepton? All of them will be minus one. So a number is given to every lepton, and we called every lepton has a lepton number of a plus one. This is the identity given to a particle. Like when I say a particle has a lepton number of plus one. So what are the chances? It might be electron neutrino, tau neutrino, muon neutrino. Like if I say in a classroom, a students with a height of 180 or 170 centimeter. So once exactly 170 centimeter, there will be specific number of students, not the whole classroom. So we give them an identity that these particles have an identity of a plus one, which is a lepton number. And all other particles which are not lepton, their lepton number is zero. Like example, if I say up, is up a lepton? No. So its lepton number will be zero. If I say down, is down a particle? It's a lepton? No. So its lepton number will be zero. Why these lepton numbers are given? These numbers are given to check the conservation, like whether this reaction can happen or this change can happen or no. Like if I say that in a beta emission, if you remember, in a beta negative beta decay, what happened? A neutron break into proton and electron. So this, we say this happened, but can we prove this happen or no? Actually, you are not learning the full equation in IGCSE. There is another particle which is an electron neutrino, anti-electron neutrino. This is a full equation. How we know that this is happening? Because we check what? We check the lepton number. Lepton number should be conserved for any interaction to happen. Neutron is not a lepton. Neutron is made up of what? It is made up of up, down, down. So it is made up of quark. Quarks have a lepton number 0. Proton is not a lepton. It is made up of up and down. So the lepton number is 0. Electron has a lepton number of a plus 1. Anti-electron will have a lepton number of -1. So is this interaction lepton number conserved? Yes, because left hand side was 0, right hand side is also 0. So it means this equation is true. So if we want to check any change, like any equation which is written in terms of the particles, that whether the equation is right or a wrong, so this is one of the way. It's not like lepton number is only way. It is one of the way to check the interaction is possible or no. Like if I say that a neutron breaks into proton and electron, is the lepton number conserved? This is 0, this is 0, and this is plus 1. So lepton number is not conserved. Means this is not the right equation what you have studied in IGCSE, that a neutron breaks into proton and electron. Actually what happened in the nucleus, when the beta emission happened, a neutron breaks down into proton, electron, and anti-electron neutrino. So three particles are actually, it releases as compared to what you have studied too. So that equation was not correct what you have studied in IGCSE. This is the right equation. So then we have the quark family. The 6 quarks are there, which is up, down, top, bottom, charm, and strange. And they experience a strong nuclear force as compared to these are the quarks. This is in terms of order of their masses. You don't have to memorize anything about their mass. This I just took a table from the Wikipedia. I also mentioned here that you don't have to memorize. And this is like you have studied the unit of the mass is kilogram, gram, milligram. But this is also one of the unit of the mass, mega electron volt per c square. This is a unit of the mass. So you can see this I write them in order of their masses. Up, down, strain, charm, bottom and top. Which particle, which quark you think took the longest time to detect? Like we detected very late. See this table, analyze this table, and which particle you think we took longest time to detect? Most of the students are saying up. Okay, good. Anyone else want to add up? Which particle? Just your guess. Which particle you think we took longest time to, or it was only recently it was discovered.
Uh,
Recently, when I'm saying, it does not mean like now, it means before 5 years. Recently here also refers to decades. So which particle you think? So everyone answer up. One student answer top, rest all of them answer up. So correct answer is actually top. Why top is the right answer? Because to produce these particles, to see these particles, we need energy. We want interaction of the particle at very high speed. So at the start, when we use a particle accelerator and we collide the two particles with each other, the particles collision were there, but they were not producing enough energy to produce a heavy particle. Because if I want the heavy particle, I need what? I need more energy. So recently, because we have now more sophisticated hadron colliders, more sophisticated particles accelerator. So as we accelerate the particles at a very high speed, so they have more energy during an interaction. Greater the energy the particles have, greater the mass of the particle can be produced. That is why the top quark is like in terms of the quark finding the quarks, the top quark took the most recent one, okay, because it has the greatest mass. So if I want to detect a particle which is having a mass of 1 kilogram and I want to detect a particle which is having a mass of 5 kilogram, which one like or produce a particle with a mass of 5 kilogram, which one I need more energy? For a 5 kg, I need more energy. So that is why when we interact the particles at a very high speed, okay, so the top quark, it is having massive or more mass. That's why it discovered late as compared to other quarks. And for every quark, there is an anti-quark. Then the combination is also there for the quarks. I will just change a flow chart to make it simple. The particle is basically a totally different, when we talk about the fundamental particles. So fundamental particles are divided into two categories. One is called a quark family. Another one is a lepton family. The quark family consists of what? The quark family consists of up, down, top, bottom, charm, strange. And or anti-up, anti-down, anti-top, anti-bottom, anti-charm, and anti-strange. The lepton family consists of electron, electron neutrino, tau, tau neutrino, muon, muon neutrino. Like I do the antiparticles first, then we have the particles. The quark family, the combination of quarks are also there, which are not fundamental. This is fundamental, but then there we don't find like there are single quarks as well, and there are combination of the quarks. The combination of the quarks, sometimes we observe two quarks together. When we see two quarks together, what we call them as mesons. And when two quarks are together, one is always a quark, another one is an anti-quark. So mesons consist of quark and anti-quark. And mesons are made up of two quarks, which one will be quark, another one is anti-quark. And we also find a quark in the combination of three, but it is not like all should be like one is quark, one is anti-quark. No, all should be quark or all should be anti-quarks. What we call them as a baryon. So three quarks are called baryon, two quarks are called mesons. And together, like collectively, the meson and baryon have a name. The mesons and the baryon collectively what we call them as hadrons. Hadron is a term which can be used for meson, which can be used for baryon. But if it is a meson, it will be a quark and antiquark. If it's a baryon, it will always be a combination of three quarks. Okay. So if I say up and anti down, what is this? Meson or baryon? Meson, because up and anti down. When I say up, up, down, what is this? Up, and down. Proton, and so basically it's a baryon. So proton is a baryon. Because what is proton? This is a proton is made up of quark, and three quarks are there, up, and down. So proton is a baryon. Same thing when I draw up, down, down. What is this? Neutron. Neutron is also a baryon. So neutron and protons are baryon. So baryon means three quarks, meson means two quarks, in which one should be quark, one should be antiquark. And hadron means we can say them together. So this is a flow chart. Now you will understand better. Like a particle can be a lepton and a quark family can be hadrons. Hadrons can be baryon or it can be mesons. An example, proton and neutrons are baryon, and pion and kaon you have heard first time, but these are also particles called mesons. And then leptons are the six of them: electron, muon, tau, and their neutrinos and their antiparticle. So this is basically a core of a particle physics. A particle can be a quark or quark or a lepton. If it is a lepton, it is only 12 possibilities. If it is a quark, again 12 possibility, and then there are further combination of the quarks, which are baryons and mesons.